Hey, good morning, everyone, or good afternoon, I should say. It's Friday, January 13th, and we have a nice long 3-day weekend ahead of us. So I just want to remind you, we have a quiz the next time we have class, which actually will be Wednesday. So that's a pretty long way off. Before we start the quiz, I will just take a couple minutes to review things, refresh your memory. But most important, you need to make sure that you know the properties and that you know the definition of a logarithm. So the quiz won't be hard if you know that stuff, if you take time to look at that stuff. So the quiz will consist of condensing and expanding like we did on the worksheet, and then also evaluating logarithms like log base 2 of 16 equals 4. Okay. Excuse me. So that quiz will be Wednesday. Okay, so before we get started, I'm trying to make sure that I remember to do a devotional or pray beginning of each class. So please make sure that everything is closed and you're not being distracted by anything. Your iPad should be closed and on the floor or in your backpack. Cell phone should be in your spa. Excuse me. Okay, the cell phone should be away in the spa. If you have not already done so, please get up and do it now. And I need your pencils down, and I need you to take a deep breath and focus so that you can pay attention. Okay, so today is January 13th, so our reading today is from Luke 24, verse 32, which says, "They asked each other, 'Were not our hearts burning within us while he talked to us on the road and opened the scriptures to us?'" Can an ancient book that was written by many people over the course of many centuries have anything to say to us today? Is the Bible's message honestly relevant? Yes, it is, as millions of believers around the world would attest. If anything, in fact, it's more relevant today than ever before, as we see the storm cloud gathering and events taking place that herald the second coming of Jesus Christ. As the Bible says, our salvation is nearer than when we first believed, in Romans 13:11. But the Bible is as up to date as tomorrow for another reason. It alone answers the deepest questions of the human heart, questions that have not changed over the century. Who am I? Why am I here? Where did I come from? Where am I going when I die? How should I live? Only the Bible gives us firm answers to these questions. And the reason is because it is God's word, given by him to guide us and to point us to Christ. Well, that's a great reminder, especially considering conversations that we've had recently. Okay, let's pray and then we'll get started with our lesson. Our Heavenly Father, I thank you so much for giving us words that were written thousands and thousands of years ago, and it's just a demonstration of your omniscience, that you knew what human nature is and how our minds and hearts would be and where we'd be today, and that we would need those guiding words, Lord. I thank you for that. I help us to remember that you are the omniscient God, and that you are all-knowing, and that nothing is surprising you, Lord. And we praise in Christ's name. Amen. Okay. So we're going to look at some applications of word problems today, just a little bit anyway, applications of logs. I do not have this in print for you, so if you want to take a moment to copy this problem down, I'll actually go ahead and expand it. Okay, so this is an example of a log equation being used for the Richter scale. And this is a very common type of log problem. The Richter scale uses logarithmic curves and logarithmic functions. So the R stands for the actual magnitude of the earthquake. A is the amplitude, T is the period in seconds, and B accounts for the weakening of the seismic wave, right? So you're going to get some sort of wave going on here that the earthquake is being represented by, right? And if you remember from science class, right, your amplitude is how high it goes. The period is how long it takes for the wave to pass by that spot again. And then, of course, B is going to be the distance from the epicenter, or an adjustment to that, okay? So determine the earthquake magnitude when the amplitude is 250 nanometers. Okay, so 250, so we're looking for R. So it'll be log, right? 250 is the amplitude, so that's 250 over a period of 2, so over 2, plus 4.25. This is just a real simple word problem because we're just going to use our calculator to get the actual magnitude. So we are looking at log. Remember, log is to the left of the 7. 250 divided by 2 plus, I forget what it was now, 4.25. And there we have a magnitude of 6.3. Please make sure that you have your calculator out and that you are doing this with me so that we can troubleshoot if you're having any trouble entering the log into your calculator. Okay. Okay, so that was a real simple example because we really just had to plug the numbers in our calculator and it made it nice and easy. Okay, let's look at another one. Let's see. Okay, I'm going to skip that. Okay, so this one is an example of how light intensity is measured in this particular case, Lake Superior. This number is going to change based on the particular lake. Of course, each lake is not going to have the same water quality or the same clarity. So this formula is a formula that we can use to measure the light intensity in lumens. In other words, how much light is penetrating the water at different depths. So at 15 feet, let's see if we can calculate the light intensity at 15 feet. So that means we are trying to solve for I. And again, if you need to pause the video to copy the problem down, you can do that. Okay. So this is going to be log I over 12 equals negative 0.0125. Now the x refers to the depth in feet, so we times 15. Okay, that's the equation that we have, and that's the equation we're going to try to solve. Now, notice there's no base written there. If there's no base, then we assume it to be a base 10. Oops, I meant to multiply this out. Sorry about that. Let's see, negative 0.0125 times 15. Okay, so negative 0.0125 times 15. And that gives, whoops, negative 0. To say I know that's not equal to 0. Okay, negative 0.1875. Okay, it's negative 0.1875. Okay, this is the equation we're trying to solve. Now, let's just think about what we have here. First off, I know that some of you are looking at it and saying, okay, I have to multiply by 12 on both sides. Well, we can't multiply by 12 yet, because this is actually not something that we want to multiply by 12, right? What we want to do is use our properties and or definition to get that I by itself. So we could use our properties and rewrite this using subtraction, right? Or we could just use the definition. So let's go ahead and let's rewrite this, use the definition. So let me just remind you of the definition. It says that log base b of x is equal to y if and only if b to the y equals x. Okay, now let's go back over here. So in our problem, the base is 10. And then we have x. What does x equal? X equals I over 12. And then y equals negative. Oops, let me get this line out of the way a little bit here. There we go. Y equals negative 0.1875. So applying the actual definition of the logarithm, right, we have b equals 10, x equals I over 12, and y equals negative 0.1875. So now let's put that into the exponential form. So b to the y, so that would be 10 to the negative 0.1875 equals x. So equals I over 12. Right, so now we can multiply both sides by 12. So 12 times 10 to the negative 0.1875 equals I. So we use the properties of logarithms, or the actual definition of the logarithm, to solve this equation. All right, so we're going to get 10 to the power of negative 0.1875. Oops, I forgot to multiply by 12, didn't I? 12 times 10 to the power of negative 0.1875. And we get 7.79. Okay, so I equals 7.79. That's the intensity, right? That's the light intensity at 15 feet. And this would be lumens. Okay? So let's see here. We did one problem involving the Richter scale, which was very simple, but what I really wanted to show you here was the fact that logarithms are used in many of our scientific calculations. This one is measuring light intensity. Okay, you don't have to memorize those formulas, but you do have to know how to solve for different parts of those formulas. Okay, let's look at some other examples. So these are actually in your Google Classroom. I loaded these documents here so that you could, you wouldn't have to copy the actual problems down, okay? So we're going to start with the one that says problem 1, efficient farming, okay? So you'll want to pull that up in your, from your Google Doc. Okay, so let's take a look at that together. Okay, so the pH scale is a scale for measuring the acidity or alkalinity of a substance, which is determined by the concentration of hydrogen ions. The formula for pH is, okay, so if you notice in this formula, sure enough, we have H with the little plus sign up there. That means H. H means hydrogen. The little plus means ions, right? Hydrogen ions. where H, the hydrogen ions, is a concentration in moles per cubic liter. All right, so we get a little chemistry going on here. Solutions with a pH value less than 7 are acidic. Solutions with a pH value greater than 7 are alkaline. Solutions with a pH value of 7 are neutral. For example, plain water has a pH of 7. Okay, the hydrogen concentration of orange juice is given. Determine the pH level of the orange juice. This is pretty straightforward, right? So our pH level, we're just going to use our pH formula. Negative log. Okay, the hydrogen ions is given. All right, so that's going to be 0.000199. Okay, and all we're going to do is stick that in our calculator. All right, so this is negative log 0.000199. Let me make sure I got that correct. Okay. And we press enter. And we get, and I don't know why this is not disappearing here. Come on. There we go. Try that again. So we get 3.7 is our pH level, or pH value. Okay. Now, if it's a 3.7, is that acidic or alkaline, right? Solutions greater than 7 are alkaline, less than 7 are acidic. So this is acidic, which is no surprise because we all know that orange juice is very acidic. Okay. All right, so let's see here. Next one, the concentration of hydrogen atoms in baking soda is given. State whether it's alkaline or acidic or alkaline. So again, pH equals negative log of the hydrogen ions. So 5.012 times 10 to the negative 9. Now we're expecting this to be alkaline, right? Baking soda should be very alkaline. Let's see, 5.012 times 10 to the negative 9. Okay, negative log of 5.012. Now this EE, or this E here, it's the EE on your keyboard, or on your calculator on the keyboard, it's EE, but the E means times 10. So that's times 10 to the negative 9. If you're uncomfortable with that, you can just use the little caret for the power button. Whoops. Right? Power of negative 9, like that. Oops. Yikes. I'm just having a hard time here. Right? That's times 10 to the power of negative 9. Let's try that. Okay. And we get 8.3. Right? 8.3, that is greater than 7, so it is alkaline. Okay. Vinegar has a pH of 2.2. Determine the concentration of hydrogen ions, right? So remember our formula, pH equals negative log of the hydrogen ions. Right? So we are trying to solve for the number of hydrogen ions. Okay, so now we're going to have to do a little bit of pre-calculus. Here we go. Okay, pH of 2.2 equal negative log times the hydrogen ions. All right, so I can divide by this negative here because the negative is outside of the log. You can't divide by this number because it's inside the log, but we can divide by the negative that's outside. Okay, so this is going to be negative 2.2 equals log of the hydrogen ions. All right, Any thoughts on how we can figure out that H? Well, let's go up here. Let's rewrite this, negative 2.2. Actually, let me write it like this. Log H. I'm just going to leave it as H and not put that plus there because that can sometimes cause confusion. Okay, that is simply part of the symbol, this plus sign here, okay? Okay, so what do we know? Well, we know that this is the same thing as log base 10 of H equals negative 2.2. Okay, let's use our definition of logarithms, right? So here we have log base b of x equals y, if and only if b to the y equals x. So now we can use that definition of logarithm to change this formula right here into exponential form. And then once it's in exponential form, we should be able to solve for h. So that's going to be 10 to the power of negative 2.2, and that equals my hydrogen ions. So we have 10 to the power of negative 2.2. So that is 0.0063. We'll just round it at that, okay? Whoops, I just forgot what it was. Okay, 0.0063 is my hydrogen ion concentration. Does that number make sense? Let's see, this is a very low pH value. Right, this one was 3.7, and you can see our hydrogen concentration, right? So this number does make sense, okay? Okay, so you see now we've seen a couple examples where we have solved the equation by using the definition of a logarithm, or we have solved for this variable, which is the x, right? We've solved for the x variable using the definition of the logarithm. Okay. Okay. Let's determine the hydrogen concentration ions in lime water. So I'd like you to do this one by yourself. So go ahead and pause the video, and then we'll do it together. Okay, so let's do this together. All right, let's write our formula down once again. We have that the pH equals negative log of the hydrogen atoms. So in this case, we're being told that our pH is 12, and it's negative log hydrogen atoms. So we're going to divide by negative 1, so we get negative 12 equals log of the hydrogen atoms, okay? Excuse me. Remember, this is base 10. So putting this into exponential form, 10 to the negative 12 equals the hydrogen atoms. Okay, so we can actually just leave that number like that. Okay, or we could go ahead and figure out what that is, 10 to the negative 12. Okay, well, that's a very, very small number. So we're just going to leave our answer just like that. Okay. Okay. The pH level of soil is used to determine which plants will grow best in an area. Okay. Let's see if I can get this to zoom. Okay. Different types of plants and vegetables require varying degrees of soil acidity. Generally, the soil tends to be acidic in moist climates and alkaline in dry climates. The chart shows the optimal pH levels, soil levels of a variety of fruits and vegetables. Okay, so here's the optimal pH levels for these fruits and vegetables. A farmer measures the hydrogen ion concentration of the soil to be 6 times 10 to the negative 7th moles per cubic liter. List the crops that the farmer can grow in this type of soil. All right, so we're looking for, we've got hydrogen ions, so we have to convert the hydrogen ions to pH level. Okay, so pH, right, we're going to do, oopsie doopsie. Okay, pH, so we're going to do negative log, and then the hydrogen ion level is 6 times 10 to the negative 7. So we're going to put that in our calculator, right? Negative log 6 times 10 to the negative 7th. Okay, did I get that right? Yes, okay. So that means we're looking at a pH level of 6.22. All right, so which type of plants would work well in that soil? Avocados, beets, 6.22, right? Onions, just barely, right? Peppers, potatoes, raspberries, spinach, sweet corn, and yams. And then you can even see which ones are more optimal. Like, it looks like peppers, potatoes, raspberries, spinach. They're probably going to work out better. Beets, right? Because the 6.22 is falling smack in the middle for those. Okay, so that's a excuse me. That's kind of a cool application. Okay, determine the range of the soil's optimal hydrogen ion concentration for growing onions. So growing onions, we're looking at the range. So that's going 6.2 to 6.8, okay? So if I have a 6.2 pH, right, pH of 6.2, what is the optimal hydrogen concentration there, okay? So we're going to look at negative 6.2 equals log, I'm just going to call it H again instead of putting the plus up there. And this is a base 10. So we're looking at 10 to the negative 6.2, right? And then the other end of that is 6.8, right? So you can kind of see what that's going to be, right? 6.8 equals negative log of hydrogen ions. So we're looking at negative 6.8. So putting it into exponential form, 10 to the power of negative 6.8 would be our hydrogen. So we're going from 10 to the negative 6.8, right? We want to be greater than that, but less than 10 to the negative 6.2. Okay? That would be the range of our hydrogen ions. So you should be getting the idea here, okay? The farmer wants to plant spinach, carrots, and beets. She measures the hydrogen ion concentration at 3.16 times 10 to the 6th polar. Is her plan feasible? Explain your reasoning. Okay, so is her plan feasible? So we know the hydrogen ions. We don't know the pH. So we have to figure out the pH. So pH, we are negative log of 3.16 times 10 to the negative 6. Negative log of 16 times 10 to the negative 6. Okay. And that comes out to 5.5. So the pH in this soil is 5.5. So is it going to be feasible to plant spinach, carrots, and beets? So let's check that out. We have a pH of 5.5. All right. So it's not going to be good for beets, right? It's going to be below the pH level. Carrots, that'll be okay. Spinach, that'll be okay also. But beets is going to be questionable. Okay. And again, I just want you to get the feel for working with these problems that involve logarithms. Okay. All right, here's another type of application. And we've worked with some of these formulas before, but we've worked with them in problems that did not involve logarithms. So let's look at this. Gina's top client is a pro football quarterback. On her website, Gina claims that since she began managing his account 3 years ago, his online followers has grown to 105,326. If he had 4,125 online followers when he hired Gina, at what monthly rate did his number of online followers grow? This is a PERT problem, right? This is just like the population problems that we did earlier this year, and it's a continuous growth, right? So that's what makes this a PERT problem. And what I'm trying to find in this problem is the R. I'm trying to find the monthly rate. Go back and say pro quarterback began 3 years ago. Okay, we're looking for a monthly rate. So we want to keep that in mind because that means we're going to use the month as the time period. All right, so what's the A? Excuse me. The A is the current amount. So A is going to be this 105,326. And that equals P. Well, P is the original amount, and it says he had 4,125 followers when they began, times E to the R times T. Now, what's T? Well, again, we're looking for a monthly rate, so it's going to be 3 years, but in months. So that's 36 months. Okay. So let's go ahead and divide by 4,125. E to the 36R. Okay, 105,326. Divided by 4,125. And we get 25.53357576. Okay. 25.53357. Was that 56? 576. Okay. Now I'm writing that out, but to be honest, I would just leave that as a fraction. Okay, but again, I know we get scared of fractions. Okay, now I am trying to solve for this R right here. So the trick I'm going to use is I'm going to take the log of both sides of this equation, right? As long as we do it on both sides, okay? And in fact, when I write this, I'm going to write it in the fraction form, okay? Because it's going to be more exact. I'm taking the log of both sides. So this is one of the tricks that we use when we're trying to solve for that variable in the exponent, right? And this equals, okay. Now let me explain what we did. We're taking the log of both sides. Now, because this is base E, I'm choosing to use the natural log. We don't have to, but it's going to make the problem much easier to solve. Okay, so I'm trying to solve for that variable that's in the exponent. Because the base is an E, I'm using the natural log. Now, I went back to using the fraction instead of this number here because it's clear to me that this number has been rounded, okay? So just to make things a little more accurate, I'm going to leave it in fraction form. So I'm going to go ahead and erase this right here. Okay. All right. So how are we going to solve this? Well, let's use our properties of logarithms, right? So I have the natural log of 105,326 over 4,125 equals, now my properties of logarithms say that I can move that exponent, the 36r, in front of the natural log. Okay. What does the natural log of E equal? It equals 1. So I have the natural log of 105,326 over 4,125 equals 36r. So now to solve for r, I'm going to bring it up here, right? To solve for r, I've got the natural log of 105,326 over 4,125 divided by 36. Okay, we divided both sides by 36. Okay, so let's do that on our calculator. Let's see, we're going to do the natural log, 105,326 divided by 4,125 divided by 36. So I get a monthly rate of 0.089999. I think we can round that to 9. So R is equal to 0.09 or 9%. So that means that the number of followers is growing at a rate of 9% per month. Okay. Okay. Write an exponential function to represent the number of online followers the quarterback will have. Okay, so we've got A equals P ERT, right? We have PERT. So my exponential function can look like this. A equals P, well, what was P? 4,125 times E to the 0.09 T. Okay. Okay. We're not going to fuss about that one right now. Excuse me. Okay. How long will it take the quarterback to double his current online following? Okay, so what's double, right? Double 105,326. Okay, and let's see, 105,326 times 2. 210, 652. All right. So we're looking to know how long it'll take to get to that point. All right. We're using the equation that I just wrote up above. So it's a very similar problem, right? I'm trying to solve for time. So we are going to divide by 4,125. So remember in this first part, part A, right, we were solving for R, which is in the exponent position. Now we're solving for time, which is also in the exponent position. So it's a very similar problem. It's e to the 0.09t. So what do we do? Well, we're going to take the natural log of both sides, and we're using natural log because of the e. Remember, you have to do it to both sides, right? You can't just do something to one side. Okay, now we're still trying to get that t by itself. So let's go ahead and bring the 0.09t in front. So we're not doing anything to the left side. So now we're on the right side. We're going to bring the 0.09t in front of the natural log. Okay. And then we know the natural log of e is equal to 1. So that means now we have the natural log of 210,652 over 4125 equals 0.09t. We're going to divide by 0.09. So I'll bring it up here. So the natural log of 210,652 over 4125 divided by 0.09 equals t. All right, let's do that on our calculator. So that's the natural log of 210,652 divided by 4125 divided by 0.09. 43.7. 43.7 is t. Well, 43.7 what? Well, that's going to be months, because that's what we used when we were solving for the rate. So it's going to be 43.7 months. And we're done. Pretty cool, eh? Okay. Let's see. All right, let's move down here to problem. Actually, you know what? I'd like you. Yeah, no. Okay, forget it. I'm sorry. Let's move down here to problem number 3. Cracking the case, because this is a fun one. All right, let's see. How much time have I been talking? Is that it? Really? Nah, it can't be true. Okay. Let's see. A coroner uses a formula derived from Newton's law of cooling right? We like Newton's law of cooling. That's kind of fun, right? This is Newton's law of cooling. This is not his actual law of cooling, okay? Newton's law of cooling was used to derive this formula, okay? And we don't have to go there right now. Capital T is the body's measured temperature in Fahrenheit degrees. R is the constant room temperature. And T is the elapsed time since death in hours. So this formula is used to calculate the amount of time since a person died. So like a coroner would use this formula. So at 8:30 a.m., a coroner was called to the home of a person who had died. The constant temperature of the room where the body was found is 70 degrees. At 9 a.m., the body's measured temperature was 85.5 degrees. Use this body temperature to estimate the time of death. Okay, so if we go back to our formula, right, lowercase t is the elapsed time since death in hours. So to calculate the time of death, that's what I need to figure out. I need to figure out the lowercase t. So we have t equals -10 times the natural log of, right, uppercase T, that's the body's measured temperature. So the body's measured temperature is 85.5 minus R. R is the room temperature or the surrounding temperature. And it says the temperature of the room where the body was found is 70 degrees over 98.6 minus R, which is 70. Okay. Maybe it'll help if I write those things out. Okay, we're trying to find T. Now the uppercase T, which is the body's measured temperature, is 85.5. Uppercase R, the temperature of the room, is 70 degrees. Okay, so that means that T is -10 times the natural log of, let's see, 15.5 over 28.6. Okay, so let's do this on our calculator. -10 natural log 15 I forgot that fast, 0.5 divided by 28.6. And that gives me 6.126, or we'll say 6.313. So T, we're just gonna round it, approximately 6 hours. So according to our calculations, the body has been dead for 6 hours at 9 a.m. So what time did it die? Approximately 3 a.m. It's actually a little bit earlier than that, right? Because we're looking at 6.13, right? If you want it to be real exact, but I don't want to get hung up on things right now, okay? Approximately 3 a.m. Okay, a more accurate estimation of time is found by taking 2 or more readings, averaging the calculated time of death. Okay, so now that I'm reading that, I'm like, okay, we have to be a little more precise. So let's be a little more precise. Okay, we're looking at 6.13 hours. Okay. Well, we know that 6 hours, right? 6 hours would bring us to 3 a.m., right? 9 o'clock is when all the temp measurements were made. Subtracting 6 hours brings us to 3 a.m. Now I have to figure out this 0.13 of an hour. 0.13 hours. How many minutes is that? Right? So that's going to be times 60. Right? So 0.13 times 60. And that gives us 7.8 minutes. 7.8 minutes. Okay. So we're at 3 o'clock. We've got to take another 7.8 minutes off of there. So that's good. If it was 7 minutes, it would be 2:53. So it's 7.8 minutes. So it's actually 2:52.2, right? So we're going to say approximately 2:52 a.m. Okay, that's more precise than the 3 o'clock. 2:52 a.m. Okay, so a more precise estimation would be found by averaging 2 or more times. Okay, at 9:30, the body's temperature was 82.9 degrees. All right, so again, right, that is the uppercase T. Uppercase T is 82.9 degrees. Uppercase R, this is a constant temperature, it said in the description above, is 70 degrees. Okay, so our formula, T equals -10 natural log of T minus R over 98.6 minus R. Okay, so let's find the T, the time in this example. So that's -10 natural log of 82.9 minus 70 over 98.6 minus 70, which gives us -10 natural log of 12.9 over 28.6. Okay, let's see what we get with that. Just pull this one down. And this is going to be, please do this on your calculator with me so that we know that you can do it. You should have your graphing calculator out and be doing the calculations with me. Okay, that gives us 7.96 hours. T equals 7.96 hours. Okay. Well, what time would that be? Okay, let's figure out that time. We said this time measurement was taken at 9:30 a.m., right? 9:30 a.m. Well, 7 hours would bring us to 2:30 a.m., right? But it's 7.96 hours, so let's figure out the 0.96, right? 0.96 times 60. How many minutes is that? That is 57.6 minutes. Okay, so 60 minus 57.6 brings me to 2.4 minutes. Okay, so it's almost another hour, right? But it's another hour plus 2.4 minutes, right? So instead of 1:30, it would be 1:32 a.m., right? So that's what the reading says at 9:30. At 9 o'clock, we were estimating 2:52. So there's a significant difference. So what we can do is average the times, right? So I had 7.96 hours plus, where was it? 6.13 hours. And we're going to divide by 2, right? 7.96 plus 6.13, dividing by 2. And we get 7.05 hours, approximately 7.05 hours, okay? 0.05 hours is how many minutes? Right, that's 3 minutes. Okay, 7 hours, 3 minutes, right? 7 hours, 3 minutes. So where does that take us? Okay, so if I'm starting at 9:30, 7 hours brings me to 2:30. Taking another 3 minutes off of that, that's 2:27 a.m. And that's a good estimation when you consider the 2 times that we got. Okay. Okay. Let's move on. Assuming the body remains in a room with a constant temperature 70 degrees, determine the temperature of the body after 24 hours. All right, let's look at our formula again. Okay. All right, so we're looking at 24 hours. So lowercase t is 24, right? Uppercase R is 70, and we're trying to figure out uppercase t. So we have 24 equals -10 natural log of uppercase t minus 70 over 98.6 minus 70. Okay, so let's see what we can do to simplify this. So I'm going to divide by -10, so that's -2.4 equals natural log of t minus 70 over 28.6. Okay, we've got to solve for that uppercase t. Any thoughts on that? Okay, yeah, let's put this in exponential form. Right, so this is the same thing as, let's say, -2.4 equals log base e of t minus 70 over 28.6. So putting it in exponential form, right, we have e to the -2.4 equals t minus 70 over 28.6. Right, now that we put it in exponential form, we should be able to solve this. So let's just kind of move it up here. Okay, I'm going to multiply both sides by 28.6. Okay, so once we got to this point here, we can put it in exponential form. Okay, let's add 70. So 70 plus 28.6 e to the -2.4 equals t. Okay. Now I'll go ahead and put that in my calculator. So we're looking at 70 plus 28.6 times e, I forget what that was now, to -2.4. Okay, let me make sure I have that right. Okay, and that gives me 72.59, or we can just say 72.6. 72.6, assuming the body, right, determine the body's temperature after 24 hours, 72.6 degrees Fahrenheit. That is our estimate of the body's temperature after 24 hours. Okay. When will the body's temperature drop to 60 degrees? Okay. Again, let's look at our formula. Okay, there's our formula. This time I'm trying to find the lowercase t. So we've got lowercase t equals -10 natural log of, right? When will it drop to 60 degrees? So that's 60 minus 70 over 98.6 minus 70. So t equals -10 natural log of -10 over 28.6. Okay. Now, this is something we haven't really talked about. We have a problem right here. Okay. You cannot take the log of a negative number. Right? Let me just back up and let me just give you something that you're familiar with. Right? Log base 3 of -9 equals x. Okay? If I put that in exponential form, that is 3 to the x equals -9. How do I raise 3 to a power and get a negative number? I can't, right? I can't. It's impossible, right? You cannot take the log. It doesn't matter what base it is. Does not matter. You cannot take the log of a negative number. So keeping that in mind, when I look at this problem that I'm trying to solve here, this is not possible. Okay, this -10 out here, that's no problem. That's no big deal. But if I try to put this natural log in my calculator, right? Natural log of -10 divided by 28.6. Okay. Oh, excuse me. I get an imaginary number. Let me go take my mode out of here. Let me put it back in the real number mode. Okay, let me do it again now that I'm in real number mode. Okay, I get an error message. Okay, so you can't do that. That's where the problem is. Even if it was just the natural log of -10. Okay, natural log of -10. It's not going to work, right? Be careful. See up here, it looks like it works, but that's because I got this I here. I got an imaginary number, so I had to change my mode. I had to put it back. It was on this a plus bi. I had to put it back in the real number mode. Okay, so this is not possible. So now let's answer the question: when will the temperature of the body drop to 60 degrees? It never will. And if you think about it, if the room is 70 degrees and it stays at 70 degrees, the body's never going to drop to 60. You're going to get that equilibrium, right? The body can drop to 70 degrees, right? But it's not going to drop to 60 degrees. Okay. Okay. Let's see here. Let me see, how much time do we have left? Okay, all right. I think we're going to stop there today. We did some pretty challenging stuff. Okay. I would like you to try to do, I think that's the last one, right? Try to do this number 2. This one right here. And then also these couple up here that we did not finish talking about. Gina, number 4, 5, and 6. Okay, so there's 4 questions that I would like you to do. We will not have a homework quiz on this. Okay, but there's 4 questions I'd like you to go back and do for homework. Okay, I will see you Wednesday. And don't forget, we have our quiz on just the basic properties of logarithms and basic evaluating.